In today's honors pre-calculus video, we'll be talking about triangle trigonometry, and not right triangle trigonometry, but just for general triangles. So this includes acute triangles and obtuse triangles as well. So assuming you already know right triangle trigonometry, which includes sine, cosine, tangent, their reciprocals, and their inverses, we can jump right into general triangles. There are four main things we're going to cover in today's lesson: the law of sines, the law of cosines, the area of a triangle using trigonometry, and solving a triangle. Now, in solving a triangle, we're also going to talk about one other key caveat, which is the SSA case for the law of sines. So all of that might sound a bit foreign to you, so without further ado, let's get started. We're starting with the law of sines. So in any triangle, we can determine a relationship between the angles and the sides. So let's just say it's A, B, C. So the side lengths are A, which is opposite to angle A, B opposite to angle B, and C opposite to angle C. We can determine a relationship between these using sine, and the proof is simple. We just draw an altitude, some height h, and what we can see is that we divide it into two right triangles. So in this first right triangle, let's call this D, by the way. In this first right triangle, we see that sine of angle A is equal to, well, it's the opposite over the hypotenuse, so h over c, which means that h is equal to c sine A, multiplying both sides by c. Now in this second triangle, BCD, we see that sine of angle C is equal to opposite over hypotenuse, h over A. So multiplying both sides by A, we get h is equal to A times the sine of C. Now we have two expressions for h, so we can set them equal to each other. So C sine A is equal to A sine C. Dividing both sides by A and C, we get sine of A over A is equal to sine of C over C. And we can extend this to sine of B over B as well if we use a different altitude. So if we use this altitude, for example, we can use sine of B over B as well. We can also make it A over sine A is equal to C over sine C, which is equal to B over sine B. But this is the core form of the law of sines, and this is a simple proof as to how we found it. Now, law of cosines. Using the same triangle, we can prove the law of cosines. The law of cosines is similar. It determines a relationship, except it uses cosine instead of sine. So the proof for this is similar. Again, we draw a altitude, call this D, height h, and let's say this is some value x. AD is x, and let's say this is y. CD is y. We know that cosine of A would be x over C, adjacent over hypotenuse, and cosine of C would be y over A. So now, multiplying both sides by C in the first equation and A in the second equation, we get x is equal to C cosine A, and y is equal to A cosine C. Now we run into a bit of problem. We see that x is equal to C cosine A and y is equal to A cosine C, but there's basically nothing we can do after that. Well, as it turns out, we actually don't need this second equation. Instead, we can use something from the law of sines and find an equation for h using the right triangle ABD. We got h is equal to C times the sine of A. Remember, this is from the law of sines proof, so I could have written sine of A is equal to h over C and then multiplied both sides by C, but we already seen this once. So now what do we do from here? Well, we can use the Pythagorean theorem, x squared plus h squared, or we can find the length of y. So instead of doing y is equal to a cosine c, we can do y is equal to b minus x, because x plus y is b, and we get b minus c cosine a. So it's not obvious at first. It's not like the law of sines proof, in which it's simple because there's just one altitude you find two equations for and solve for both. But this one you have to do a bit of logic and thinking. So there are some common pitfalls, such as finding both x and y, like we did earlier, or finding c squared is equal to x squared plus h squared, instead of finding y based on x. But here we are, we get h and y. Now we can do the same thing. We were thinking of doing c squared is equal to x squared plus h squared, but if we did that, we wouldn't get the formula. Instead, we do a squared is equal to h squared plus y squared. So a squared, and h, remember, is c sine a. Now you square that, and you get c squared times sine squared of a. And then we have to add y squared. So that'll be b squared minus 2bc times the cosine of a, using the square of a binomial. And then we have to add c squared times the cosine squared of a. Now we see here that there's a c squared cosine squared a and a c squared sine squared a. And we know that sine squared a plus cosine squared a is always equal to 1. So simplifying them into one expression, we get c squared times 1, which is just c squared. So it'll become c squared plus b squared minus 2bc cosine a, which is just one form of the law of cosines. You can also do it in terms of c squared or b squared, but this is one of the ways. You can do c squared is a squared plus b squared minus 2ab cosine c, for example. Or b squared is equal to a squared plus c squared minus 2ab cosine b. So that's the law of sines and the law of cosines. Moving on, we get to talk about area. So we all know that the area of a triangle is 1/2 base times height, but there's also another way to find the area. And area is equal to 1/2 times a times b times the sine of c. Now, like with the law of sines and cosines, I will offer you a proof. With this triangle, if you were to have that height, you would get 1/2 base times height, b times h. But remember, in our law of sines proof, we used another form for h, which was a sine c or c sine a. Any of those work. So you just replace h with a sine c in this case, and you multiply that by b because it's 1/2 base times height. So b times this is ab sine c, and then you multiply that by 1/2. So that's how you get your formula. And now actually solving a non-right triangle. So the ambiguous case of SSA is the first thing we need to talk about. So it's a case for the law of sines. There are 4 cases. Case 1 is that there's no triangle, and this occurs when A is too short to create a triangle. You'd be given A, B, and angle A. That's the side, and angle. And if you find that A is too short, then there is no triangle possible, so there's no triangle. Case 2 is when A is exactly the right length, such that it intersects this line down here exactly once and forms a right triangle. One right triangle. Case 3 is that one of the possible triangles is acute. So again, if we have A, B, and A, now A is really long, but it still intersects it twice. One of them is acute and the other is obtuse, so this is case 3. And case 4 is there's only one possible triangle and it's acute. So this is when A is much longer and only intersects this line once all the way out here. If you were to draw the other side of A, it'll go all the way here, which doesn't intersect the triangle and make it work, so there's only one possible triangle. So we have no possible triangles, one possible triangle, which is right. This is two possible triangles, one which is obtuse and one which is acute. And we have one possible triangle, which is exactly acute. So the best way to do this is just to find the law of sines and then use that to determine which of these cases it is. So let's do an example problem of solving a triangle. So let's say it is A, C, B. This side length is 15, this side length is 12, and this angle is 40 degrees. What you would do is, first step, use law of sines to find this angle. You'll get sine of B over the length B, which is 12, is equal to sine of 40 degrees over the length A, which is 15. And if you were to solve this, you'd get sine of B is approximately 0.514, which leaves measure of angle B to be 30.946 degrees. Now that's all well and good. That would be this angle right here. I'm just going to approximate it as 31 degrees in this diagram here. But that's only one of the possible solutions, or it could be. For the other one, you would have to do 180 degrees minus this angle here. So that would give you approximately 149.054. And that's the other solution, because remember, sine is positive in both the first and second quadrants, which is why this is the first quadrant answer and this is the second quadrant answer. And now you would see this is approximately 149. So 149 plus 40 is 189, and to find the third you do 180 minus that, but that's where we run into a problem. That means that this must be negative, because this is way too big already. 149 plus 40 is 189, which is way too big already, which means the second triangle does not exist, and therefore there's only one triangle. Sorry. And therefore we can remove this B1. It'll just be measure of angle B because there's only one possible triangle. Now we can find measure of angle C because we know there must be 180 degrees in a triangle. So we do 40 plus 30.946 is 70.946, and then 180 minus that would be 109.054 degrees. And then you find the third side using law of sines, for example. You can do this side would be C over sine of C, which we found to be 109. I'm just going to write it as sine of C over here, is equal to 15, we got from the start, over sine of 40 degrees. So 15 divided by sine of 40 degrees is approximately 23, and then multiplying that by the sine of 109 degrees would be around 0.945, which means this would be 0.945 times the 23. Remember, sine of 109 is 0.945, and then 15 over sine of 40 degrees would be 23 approximately. So multiplying them both, because we want to multiply both sides by the sine of c, we get c is equal to 22.057. And we were given two side lengths and an angle. We found the remaining two angles and the remaining side length. So this triangle is considered solved. You can also, if you want to find the area, some questions would ask you that. But in this case, the question didn't ask that, so we don't have to find the area. That's all there is to triangle trigonometry. Three main formulas: law of sines, law of cosines, and the area formula. And then just logic and the ambiguous case will help you solve a triangle. That's it for this honors pre-calculus video. We'll see you next time.